Hello, my name is Jojo Brooker and I'm very happy to be here. Today we're going to be looking at graphs as the model for the spread of disease. Specifically, we're going to be looking at independent cascade models. So one example of a graph might look like this one right here, where each of the nodes or vertices is a person, and each edge is an interaction, a daily interaction between two people. This could be modeling a classroom setting. So if maybe you had, for example, this was your teacher, and they had a whole network of students, and maybe some of the students were friends. And each of these students each had both of their parents at home. And maybe the teacher also has a loved one at home. If one of these people becomes infected with a disease, we want to ask, how long does it take until everybody gets infected? So if maybe this person right here gets infected, how long before everybody in their class and all of their parents and their loved one is infected with this illness? This could work for any group of people, so not just a classroom setting. Maybe it's also one of those pod settings like we had, or like some people like to do for managing the pandemic spread, where they agree that this group of people only interacts with each other. But then what if one of them decides to go to like their nephew's birthday party and maybe now is a carrier for the disease? How long until it infects this entire pod of people? Not to be dark about it. So we're saying that this person, this infected person, they can only infect the people that they're connected to, right? And these are examples where this person's connected to everybody. But what if instead of them it was this person, right? Then only these two people are at risk of getting infection, or of getting the infection. So we're saying that there is a probability P for, to simplify the problem, we're saying there's a probability P that the disease spreads from one node to each of its neighbors. That also means that there's a probability of Q, which is equal to 1 minus P, that the disease does not spread. So since this is a daily interaction, we're looking at this on a day-to-day basis. So how many days until the entire network becomes infected? So let's look at an example. I have pre-recorded our algorithm. Thank you, huge thanks to DiGioia and Mikayla Bryant for helping make this program. So over here we have what day it is, and this is our graph. And over here is the step button, and that's going to step us day by day. That is each day of running the infection. So first we draw the graph, and we draw the edges that we want. And it doesn't have to be every edge, see, because this little person's all alone, right? So let's play out this infection and see how many days. So we're starting the infection here. This is our decision, is where it starts to spread. So how many days until it spreads to everybody? So over here, I'm showing you that we have a probability set of 20% that the infection will spread on any given day. And it's only at risk of infecting its neighbors. So there we have it. On day 1, this person already got infected. On day 2, this little loner person got infected. And then on day 4, we have complete success. And a success, we're going to call a success when everybody in the graph becomes infected, because that's when the disease succeeds. So let's do another example starting from a different point. So here I am drawing the graph. And we are going to start this infection at this little node on the end. And something you can notice about this node on the end is that in order to infect the rest of the graph at all, in order for this graph to succeed, it has to go through this middle central node. So it has to succeed on that one first before it can infect the rest of the graph. And that is very interesting. So day 2, it infected this little node, and now it has a chance of succeeding on the rest of the... Wait, was that on day 2 or day 1? Okay. So day 1, it didn't infect anybody. Day 2, it infected this one person, and now it can infect the entire graph. Day 4, not the entire graph has been infected. Day 6. So notice that now both of these nodes are both going after this one healthy node. So it's only looking at the healthy nodes that are adjacent to the sick nodes. And because it is connected to 2 sick nodes, it's more likely to get sick. And boom, on day 13, we have full success of this illness, starting from the end over here. So intuitively, you might think that a graph succeeds faster or at an earlier date when it has a high edge density, so when there are a lot of edges between all of the vertices. But we suppose that we get a higher success date or a lower success date, a sooner success, depending more on the geometry of the graph. So something such as the diameter of the graph, not the number of edges that it has. So for example, let's talk about, so the edge density is measured by the number of edges over the number of vertices, and the diameter is measured to be the maximum distance between any 2 vertices. So let's look at some examples. First, I will show an example of 2 graphs that have the same edge density, but different diameters. So these will all be 5 node graphs. These are all ways of 5 people interacting. So here you can see that They both have 5 nodes and 1, 2, 3, 4, 1, 2, 3, 4 edges. So their edge density is 4/5 for both of them. Yes. However, this one has a much larger diameter, right? The maximum distance between these two nodes, or the distance between these two nodes is 4. So this one has a diameter of 4, and this one has a diameter of 2. So I calculated these in advance on the computer using our program, and I will show you how I found the values, because these don't have the infections marked, right? So let's say that there is just a random chance each node has the same probability of being chosen to be the randomly infected person. It could be anybody, right? So then is the person on the end? Well, there are 2 out of 5 people on the end. I take the mean and the variance of this graph specifically with this node, our initial infected node, and I multiply it by 2/5. There's a 2/5 chance of the node that is not quite in the middle, the one that's second from the end, being chosen, and there is a 1/5 chance that it is the middleist node. And so I find the mean for all 3 of these graphs and the variance for all 3 of these graphs, and I add them together with these weights. So for this graph, the graph of just a straight line, 5 nodes in a straight line, we have the mean date of success to be a 17, and it has a variance of 67.414. Oh, these are approximately. Yes. For this star graph, there is a 4/5 chance that one of the ends is selected, and a 1/5 chance that the centermost node is the first infected. So for this graph, we have a mean of approximately 12.8 and a variance of approximately 40.5. So as you can see, this graph with the smaller diameter has a much lower mean and a much lower variance than this graph with the larger diameter. So now let's look at some graphs with the same diameter, but different edge densities to see how the edge density changes the mean and the variance of the graph. So we're going to look at 5 nodes like this, which has an edge density of 6/5 and a diameter of 2. And we're going to compare it to this graph, which has 2 more edges, so an edge density of 8/5, and also a diameter of 2 to get from one end to another. So for this top graph, we had 3 symmetric points where the infection could have started. It could have started up here, could have started here, and it could have started here. And the mean of all 3 starting points, the mean of all the dates of succession was day 8, with a variance, approximation, with a variance of 15.6. And for this graph, it has the same points of symmetry. But for the whole graph, we have a mean date of success on day 6, with a variance of 8. So that variance is still quite a ways off, but you can see that these means, the expected date that we have success on these graphs is much closer together than the date of success from the previous 2 graphs where the diameters were different. So we're asking, does the diameter, how does the diameter affect the date of success? So let's look at some trees. So we're going to look at some trees because they're nice and simple. And you got to start with the easier stuff to look at. So we're going to look at this tree. This is called the independent cascade model. And it makes our calculations a little bit nicer because, as you can see, we can only infect this entire graph if we go through the middle here, right? Which means that basically this little mini graph, this subgraph, has to succeed first in order for the entire graph to succeed. And the rest of this subgraph can't even start until this one begins. So what we have is that the expected value for, this is our gluing theorem. The expected value of the whole graph, starting from this one point, is equal to the expected value of the first subgraph, where it started, plus the expected value of this subgraph, which is going to be what happens once this graph succeeds. We can now move on to this graph. Interestingly, let me see. I want to say that yet. So this graph right here is, if we unfold it, a little tri-star like this, right? And the expected value of this star is equal to the max for each of these ends, right? So for the entire graph to become infected, each of these little subgraphs has to succeed first. So this is equal to the max of the expected value of each one of these mini graphs. Yeah, and there's a paper by Dr. Bennett Eisenberg at Lehigh University that explores these star graphs and their expected value of success. And he actually came up with an explicit equation for it, but it's really, really long. The summand for it is really long and quite difficult to work with because it has a really large sum in it. But let's look at some really small graphs and then use the gluing formula to find some more general graphs too. So to start off, we have this little mini graph that we were actually just talking about. And we do actually have an equation for it. So for this little graph, we have that our mean, which from now on I'm going to write as mu, is equal to 1 over p, where once again, p was our probability of this spread infecting on from one sick person to one healthy person. And our variance, sigma squared of q over p squared, where q, once again, is the probability that it does not spread, that we go on a day without the infection spreading. And we calculated for this line, aligned with an extra bit attached to it, the mean mu is equal to 2 over p, and the variance is equal to q over p squared. No, 2q over p squared. And you'll notice, hey, that looks pretty familiar, and that's because of our gluing theorem. And what our gluing theorem says is that for any number of these that you glue together, if you have, let's see, in general, if you have any line graph like this with n extra nodes on the end over here, then our gluing theorem states that this is equal to, here mu was 1 over p, and sigma squared, our variance, was equal to q over p squared. By our gluing theorem, we have that the expected value of a graph with n plus 1, a line graph with n plus 1 nodes here, this is equal to n over p. And also, our gluing theorem works for our variance. And it says that our variance is additive when we glue. So the variance of this same general line graph is equal to nq over p squared. in fact, when we calculated this, we did an example of n equals 3, and we put it through our program, and we found the mean. And our mean that we found in the program was 15.081 for this graph starting on the end. These should all be starting on the end. For this graph starting on the end, and when we plug that into our formula here, so n equals 3, then we have 3 over, and we ran it with a probability of 20%, so 3 over 0.2, which happens to equal 15. And that was very satisfying. And we also got that our variance for this graph was was 61.497. And so when we plug this in, we have 3 times 0.8 over 0.04, and that is equal to 60. So that's also very close. Yeah. And this is a direct result of our Coulomb theorem. We also did lines starting from the middle. So those are lines starting from the end. And the tricky thing about lines starting from the middle is it's equal to the maximum date of either this side succeeding or this side succeeding. And so for this, we calculated our mu to be 2 over p minus 1 over 1 minus q squared, with our variance q times 2q squared plus 2q plus 2 all over 1 minus q squared squared. And this graph is going to be the expected value is going to be the maximum of the expected value of one side and the other side. On a similar note, we also calculated this graph, which is the maximum of one of these 3 ends, to be (3 over p minus 3 over 1 plus q times p plus 1 over p times 1 plus q squared, with a variance of all of that minus all of that squared. And additionally, we have the probability distribution function for this graph. But because we also have the gluing theorem, we know that that mu of this graph is equal to 1 over p plus 2 over p minus 1 over 1 minus q squared, and that sigma squared of this graph, the variance, is equal to q over p squared plus q times 2q squared plus 2q plus 2 all over 1 minus q squared squared. Yeah. So there's so many other applications to this and other questions that we can ask. We can ask questions like, what if there's a healing time? I know that Mikayla, Bryant equipped our program. Mikayla and David equipped our program to handle the possibility of healing after a number of days. So how long does the disease spread given that maybe a vaccine comes out? There are also other applications of this problem. This can work for the spread of really anything within a network. So for instance, it could be the spread of ideas from peer to peer, could be changing someone's mind, it could be advocating for your favorite political candidate, it could be changing fashion trends on like Instagram or something, follower networks, the spread of anything really from person to person. And anything that really spreads by exposure. Thank you very much for watching my talk.